Bismillahirrahmanirrahim. Assalamu alaikum viewers, and welcome to my channel. And in today's video we are going to understand how to approximate a function by the help of a polynomial using Maclaurins series and the Lagrange form of remainder function. So over here we are having a quite rich example in which we'll try to cover up all the aspects, how to understand the width of the accuracy, or how to understand the nature of the error or the length of the error with the help of the remainder function, and how to confirm our answer of the actual function and that of the polynomial value. So we'll try to cover up all these aspects by covering some multiple parts in the same example. Okay, so let's move ahead and try to look to the first part of our example, which is right over here. Okay, so this is the example. You can see that we have to determine the accuracy when the 7-degree Maclaurin's polynomial of a fine function, which is said to be the P7x, is used to approximate sine 0.5. So for that purpose, first of all, we'll just try to write down the general appearance of the Maclaurin's polynomial, because this polynomial is actually centered at 0, and we just try to extend this polynomial function on both sides of the 0. So that's how we just perform in the Maclaurin's polynomial. So let us write down the general form of Maclaurins, because it is basically derived from the Taylor series. So wherever we are having a in the Taylor series, and a is any real number, we know that, and we have discussed this thing quite exhaustively in our previous 2 parts. You can see in the description box the links. So there is no need to repeat the Taylor series again and again, and no need to repeat the entire thing from the very scratch. So we just write down here the general formula, in which we just replace a by 0 in the Taylor series, and we just got the Maclaurin series over here. Okay, so that's how the Maclaurin series look like. So here you go. Okay, so this is it. This 5 is quite rough. Okay, so we have just, you can see this is the general form of your Maclaurin series, and we are using here the 7th degree Maclaurin polynomial. So we are going to write down here the first 8 terms in the polynomial, and the 9th term is going to be the Lagrange form of remainder function. So you can see here, this is the general form of your Maclaurins, starting from this term ending to this term. All these things are very well known to you, as you can see. Okay. Alright, and over here we are having the Lagrange form of remainder function. We know that in Lagrange form of remainder function, as the number of terms in the polynomial is the degree of the polynomial is 7, so n is 7 here. Alright, so and f of x is sine x here. So the remainder function actually looks something like this, as you can see that the remainder function, something it looks, this is the actually the order of the derivative. You can see, so this is z upon n plus 1 whole factorial upon x minus 0 n plus 1. This is the general form of the Lagrange form of remainder function, fused in Maclaurin's form. So at the place of our a, we just replace by 0. So this is something that you call R 7x. Okay, this is it. So over here n is 7. At the place of our a, we have placed 0. So this is it. So this is it. This is your f of the 8th derivative of our f of z, and this is the 8th factorial upon x minus 0 power raised to the power 7 plus 1. This is it. So when we just try to simplify this entire series, or we just got a form like this. We just got a form like this. Alright, this is the simplified form. You can notice here. Okay, because you know that we know that it's x minus 0 simply x, so it comes out to be x power 4. So that's what we have applied in the entire in this entire polynomial form. Okay, and this is the Lagrange form of remainder function, the 8th derivative of our f of z upon 8 factorial upon x power 8. This is it. This is the Lagrange R7x. All right, and from here to here, this is the p of 7. So actually we can also express our f of x as p7x plus r7x. This is the 7-degree Maclaurin polynomial, and this is the remainder function of the Lagrange form. All right, f of x is sine x and n is 7 here. We have to find here what? We have to find here the accuracy of the function sine of x with respect to the 7-degree Maclaurin polynomial as it is asked over here. So we have to find out the nature of r of n, r7x here, what it gives actually. So for that purpose, because r7x actually explains us the difference between the actual value of the function sine x and the polynomial series, Maclaurin's form. So it is the difference or the error that is so explained by this remainder function. So remainder function is over here. It is 8 upon 8 factorial upon, and x value is 0.5 here as it is mentioned in the question. It is 0.5 here. So the x is 0.5 here. So at the place of our x, we just write down here 0.5 at this place. Okay, so that's it. So first of all, let us try to find out, my z is quite horrible here. Let us try to find out all the eight derivatives of our sine of x one by one, and then we are going to replace our x by 0 in order to get the values of these terms. Okay, so let us find this thing manually one by one. Let's see what we get. So here you see that's f of x is sine x, so f of 0, we are just going to replace our x with 0. And sine of 0 is 0. Now let us find out the first derivative of this function. For the first derivative, which is actually cosine x. Okay, and we just f dash of 0 is going to be cosine of 0, and it is 1. Alright, so we just keep on doing this thing. The second derivative of this function is, though I'm not going to write the operators again and again, but just writing the first two, and that's it. So it is negative sine of x. So f double dash of 0 is minus sine of 0. So it is said to be 0, nothing else. Third derivative is the derivative of this thing. It comes out to be minus cosine x. We just get minus 1 here. Okay, in the same way we are going to find out all the 8 derivatives here. So let us try to finish up quickly. So you see we have just completed here all the derivatives from 4th degree up to 8th degree. So we just did that entirely, and over here we just replace the x by 0s up to 7th derivative, and we just got these answers. As far as the 8th derivative is concerned, it's something that is used in the Lagrange form of remainder function, and over there the x is replaced by z, so we just did that. Okay, now we are going to substitute all these values in the Maclaurin's polynomial p7x form, and then let's see what we are having there. So here f of x is equals to f of 0 is 0 plus f dash 0 is 1 into x plus this thing will become 0 plus f triple dash upon 3 factorial 1x cubed. Okay, and then the 4th becomes 0, and then the 5th become 1 upon 5th factorial x power 5, and then 6 will become 0, and then 7 becomes minus 1 upon 7 factorial x power 7, sorry. Okay, plus, and then the Lagrange form is f 8th derivative of your f of z is sine of z upon 8 factorial into x power 8. That's it. So let's try to write the final form. X minus x cubed upon 6 plus x5 upon 120, because 5 factorial is 120 here, minus x power 7 upon 7 factorial is 5040. Yeah, that's it. Plus, and plus sine of z upon 8 factorial, and 8 factorial, whatever it is, we're not going to write the value here in numerals, we just rely on 8 factorial, that's it. So it is into x power 8. This is the final form that we are having. This is the 7th degree Maclaurins. This is P of 7. This is your P7x. Okay? And this is your R7x. Alright? Plus. And f of x is your sine of x here. That's it. Okay? So now we have to find out R7x. So R7x is actually what? It is the difference of your sine of x and your P7x. So how about if I just shift my P7x over here? We are going to analyze here graphically as well, but before that we should do it algebraically. Okay, so what is going to be the accuracy between these two values? Up to how many decimal places both these answers comes out to be same? That's what they're asking us to do. And we know that our remainder function is this thing, and we are just talking about R7 at 0.5, value of x is 0.5 here. It is sine of z upon 8 factorial into 0.5 power 8 raised to the power 8. Oh, sorry, it's 5 power 8. So if you just divide this 0.5 power 8 upon 8 factorial, it gives you almost 0.601. Okay, so this is n sine z into sine z, and we know that the value of your sine, it varies between 0 and 1. Okay, so if we just put down the values between 0 and 1, and the value of our R7.5 will become less than your 0.6 times zeros and 1. Okay, so this shows that the magnitude of your error 0.5 is less than 0.00000001. If I just remove my sine z, because sine z value is between 0 and 1, so that's it. So if I just put any value between 0 and 1 and I multiply it with this value, it is definitely going to reduce. So the remainder function at 0.5 is less than this thing. Alright, so this thing shows that the difference between your f of x and your 7th degree polynomial is this. So it is going to be less than 0.000001. So this thing shows that they are going to be accurate up to 6 decimal places. Okay, so we therefore conclude that when P7 f of 0.5 and your P7.5 are calculated, these two values are going to give you a difference that should be accurate up to that should be less than this value. It means that both these answers will be accurate or will be same up to 6 places of decimals. That's what it means. So we are going to figure out in the next part later on, but this is exactly what it says. Okay, both these answers will differ up to 7 decimal place, but up to 6 decimal places they will be same. That's what it means. So the accuracy is up to 6 decimal place. That's how we just come to know with the help of this remainder Lagrange form of remainder function. So that's it. So the accuracy is up to 6 decimal places. That's it. Now let's see the next part of this example. The next part says that we have to support our answer of part A graphically. So for that purpose, what we do, that we know that over here it is written already that the remainder function or the error is the difference between the real function sine of x and the 7-degree Maclaurin polynomial. That's what it means, right? So we are going to plot here actually this function R7x on the graph paper, on the 3D graphic calculator. That's what I'm using here. And then we are going to, along with R7x, the two more things that we have to plot are actually these values. Y is equals to positive 6 zeros 1 and y is equals to negative 6 zeros 1. So let's see where these two lines and this curve is going to intersect, and then we'll try to find out that between those points of intersection is x value equals to 0.5 resting or not. If it is resting, it means our remainder function value or the accuracy is graphically, it has been substantiated, okay? It has been corroborated. That's what it means. So let's see, and let's have a look on the graphic calculator. Okay, this is basically the graph of your sine x, right? We have got nothing to do with it. Actually, we are determined to find the difference between the sine x and the p7x. So it is something this. Okay, that's how it looks like. But I have to modify my x and y scales. So I will just modify it, and I will just maintain the x-axis from -1 to 1, and the y-axis at 0.60 to 0.602. Okay, that's it. Now it is a little bit broadened, and then I'm going to draw my y is equals to negative 6 zeros 1, and it is this. Okay, and y is equals to positive 6 zeros 1. It is right over here. So you can see that these two lines intersect this curve, which is representing the error curve R7, which is the remainder function curve. They are intersecting at this point, okay, and at this point, if you just see. Okay, so they are approximately, because this point seems to be 0.5, so it is negative 0.7 approximately. This point of intersection is positive 0.7, and this point of intersection right over here is negative 0.7, if you can see. So we see the point of intersection are negative 0.7 and positive 0.7. So you see the point of intersection between this curve and these two lines is almost negative 0.7 up to positive 0.7. So your 0.5 is lying here. Okay, so it means our error value is very, very accurate, so evaluated algebraically, and it has been now confirmed graphically too. Okay, now let's see what the part C says. Now part C says that we now have to compute P7.5 to approximate sine 0.5, accurate to the number of decimal places allowed by the answer in the part A. Part A says that the accuracy should be up to 6 decimal places. Now we have to individually find out sine 0.5 with the help of our calculator. So sine 0.5 give us what? Let us see. So let's see what the sine is. Sine 0.5. Okay, so it's 8.7 10 power negative 3, and also you can write as 0.00872 like that. Okay. I'm sorry, I just forgot to manage my Casio on the radian mode. It was previously on degrees, that's why the answer was coming wrong. So now I have just set it on the radian mode, and now I'm going to calculate the 0.5 value, and the sine 0.5 comes out to be this 0.4794255 like that. So let us write down the value here, 0.479425. So if I just round up to the 6th decimal place, it comes out to be 0.479426. Okay, this is it. Now let us find out the P7.5. So wherever we are having x in the P7 over here, we are just going to replace it with 0.5. Okay. So it will be 0.5 minus 0.5 cube upon 6 plus 0.5 power 5 upon 120 minus 0.5 power 7 upon 5040. And then we are going to compute it. Let's see what values it gives. I just did that. This polynomial, I just write the polynomial over here, and I got this value. 0.47942555332. Okay, so we just focus on these values 332, and let's see. Sine 0.5 was different at these positions. Okay, it was similar up till here, and then at this position I think it was different. So you can see that up to 6 decimal places they are same. Almost 7 decimal places they are same. Sine of 0.5 was, you can see at this place we are having a difference. Okay, it's 8.6 here. Okay, so that's the difference we are having. So a great degree of accuracy now it is determined. So it is going to be 0.47942555332. That's what, and it was 55386, something like that. So you can see that it is almost 0.4794255. I'm gonna say it's 6 when I round it up. It's 6. Okay, so we can see that up to 6 decimal places these values are same. So sine 5 is just fine. So basically both these values were this 55386. This was your sine 0.5, and sine P of 7, P7.5 was this. So you can see up to here the accuracy is determined. From here to here, the accuracy is determined. Okay, so 6 decimal places is 100% fine. Okay, so the thing that we did in the first part was too cool. I mean, it's very accurate, I must say. So up to 6 places of decimal up to 6 decimal places, definitely you're going to get the accuracy in both these values, means the values of the actual function and the value of the polynomial, so obtained through the Maclaurins format. So this is it. That's how we just try to find out that's how we just try to approximate any non-polynomial function with the help of the polynomial form of the power series. Okay, which is nothing but the Taylor form and nothing but the Maclaurin form. So that's all for today, and inshallah in the next video we'll try to figure out some more examples on the same topic. So if you find this video helpful, I humbly request you to subscribe my channel, hit on the like, and share this video as much as you can. I'll see you in future with more helpful videos. Take good care of yourself. Allah Hafiz.